Okay, so we were on this slide right here where we were talking about the greenhouse effect. I showed you the simulation where white light radiates down to the Earth, bounces back as IR, gets absorbed by molecules and re-released. So this is we call it the greenhouse effect because that's what they do. What happens in a greenhouse is they trap the infrared radiation in and it heats up. Another thing I wanted just to emphasize, and this goes back to when molecules absorb IR radiation, they move more quickly. If they're moving more quickly, what happens to the temperature? Yeah, therefore, does therefore have an E or no E? Therefore, temp increases. I'll crowdsource a lot of spelling. Therefore, temp increase. I read a ton, but for whatever reason, spelling just never sticks in my brain. Okay, so how are IR and heat related? Talked about the greenhouse effect, and if it absorbs, if molecules absorb, they vibrate more frequently, therefore temperature goes up. Okay, photoelectron spectroscopy, PES. When atoms absorb visible or UV light, electrons move to higher energy levels. We talked about this. That is how light and chemistry are related. That's how we know a lot about atomic structure, is by shining light on different substances and seeing what is absorbed or released. If enough energy is absorbed, the electrons can leave the atom altogether. That's the photoelectric effect. We talked about that. That's our evidence that light is a particle, right? The energy of the emitted electron is equal to the energy of the photon minus the energy used to escape the pull of the nucleus. We talked about that as well. And by counting how many electrons are released with a given amount of energy, we can determine how many electrons are in each level. So, photoelectron spectroscopy. This is like an off-the-record statement. I've never used this in my life. I had never learned this in my life. I did not know what this was until we got the new AP chemistry standard. It's not particularly useful. I think maybe there was one person on the board of the college board who has a textbook that talks about photoelectron spectroscopy, so he pushed for it so his textbook would be picked. Just a theory. So, anyway, you guys need to learn what it is. So, you're bombarding a substance with energy, and electrons are getting emitted. Now, the output from this is a graph that looks like this. You have relative number of electrons. So at this higher, this is a smaller amount of energy required. This is a higher amount of energy required. I know it says it's carbon down there. Looking at this, how else could you guess that it was carbon, given that this substance releases electrons by hitting it with light and getting them to pop off? How else would you know it was carbon if it wasn't written down? Any ideas? Yeah, go ahead, Ben. Yeah, the 3 2s add up to 6, and neutral carbon has 6 electrons. So if you're emitting 6 electrons from a neutral substance, that means it has to be carbon. Yeah. What is the unit for the x-axis? That is a tremendous question. Energy. I don't know. It might be a relative energy. And so it might be relative energy and relative number of electrons. So if you look, these are on different scales, right? The relative energy here is 28.6 whatever units. This is 1.09 and that's 1.72. So they put this scale from 10 to 100 and this from 0 to 10. The reason they do this is otherwise you might have like 2 peaks here and then one like way over here. So the question was, you can say the first 2 electrons are from the outer shell and the second 2 are from the inner. Well, okay. Now that's the key. If you're shining light, basically applying energy to a substance, which electrons will pop out first? The ones on the inside or the outside? Outside. So these are the lower energy required. Lower energy required to emit. So therefore, they are the ones farther from the nucleus. Right. So we know that there are 4 electrons in the energy level far from the nucleus. These are the 2s2 and 2p2 electrons that you are emitting. So you shine light, you emit these 4 electrons, you get the reading, and you know that these are the electrons that are emitted. You go higher energy, these are the 1s2 electrons that are being emitted. Okay. I don't really need you guys to have a lot of understanding of this. I just want you guys to be able to look at something like this if it comes up on a test and say, there are 6 electrons. It's carbon. Right? Because this is not something that you will use in your life. Yes, Noah. Okay, so the question was, how do we know if it's carbon if there's 6 electrons? You could have ions that have 6 electrons. Nope, there are no other. Only carbon, when neutral, has 6 electrons. That's the question. How do we know it's neutral? I'm telling you it's neutral. Right. So the question was, with any of the photoelectron spectroscopy diagrams, do we assume they're neutral? Unless you're otherwise told, then yes. Then I've almost never seen these ever anyway, but I've only ever seen ones that are neutral. So if that's the case, you can count the electrons. I mean, it is kind of interesting. You can get some cool information out of it, like, okay, instead of electrons just being on the second energy level, we know, oh, the second energy level is split into 2 very close orbitals, right? The s orbitals and the p orbital. So I think do you guys have one of these on your problem set, for those of you who, yeah, 1 or 2 of them. So not very difficult. You're counting electrons. Yeah, Jack. How do you know there are only 2 levels instead of 3 levels? That's a good question. You know that because you have a knowledge of chemistry that says I have 2 electrons in the first energy level and 8 in the second. Otherwise, you know, because these two, sorry for those of you, I'm going to circle. These 2 are much closer together than this one is from all the others. So you know that they have to be very, very close. They're slightly different, which is the difference in energy between S and P. Okay, Kool-Aid's law, the Beer-Lambert law. You guys did part sort of one of these a little bit when you did the light transmittance. Later on in the year, you're going to look at it in a different way. It's called the Beer-Lambert law, and this is if a substance absorbs UV light, that's UV or visible light. If a substance that absorbs UV visible light is dissolved in a solvent, and in this class we're exclusively going to use H2O, we can determine the concentration of that substance so we have something dissolved in water. We know it absorbs ultraviolet or visible light. We can determine the concentration of that substance. To do so, we need a calibration curve. This is essentially what you guys did in the lab. Except instead of absorbance, what did you guys look at? Transmittance. The math is a little different between absorbance and transmittance. So that's why you guys had to do all the graphs for your lab. The absorbance one is a little bit easier. So you guys created a calibration curve, right? You found a plot that with some mathematical manipulation was linear. And you could take that electrolyte, blue electrolyte sports drink, and put it on that curve and figure out what the concentration was, right? So you can do that here. I'm not going to show that. Where are you? Uh-oh. Oh. Does Control Z work? I guess not. Okay. So that's okay. Is there an undo option? Yeah, we're just going to try to erase this. We'll see how it goes. Eraser. Ah, good. Erase the whole thing. Okay. And now I just need the arrow. Okay, good. So here's an application of Beer's law. Similar to your lab, but different in that you're measuring, instead of transmittance, you're measuring absorbance. So what you saw is when your concentration was very low, most of the light transferred through. Here, when your concentration is very low, your absorbance is very low. Right? Low concentration means it's not going to absorb a lot of the light that's passed through it. So a student collected the data above using solutions of known concentration. She then measured the absorbance of a sixth solution and found it to be 0.454. What is the concentration of this solution? Now, you can ballpark it, right? You can look at these and say, okay, it goes up. This first one is 0.72, or 0.072, 0.222, 0.355, 0.5, 0.651. So you know it has to be somewhere in here. So if this were an AP test question, you know it has to be somewhere between 0.5 and 0.7 molar. Which one is it probably closer to? 0.7, right? Because 0.454 is closer to 0.5 than 0.355. So you know it's probably somewhere closer to 0.7. That's an AP question when you have not very much time to do each one. You have to burn through them. How you would do it on the labs is, this is Beer's law. Remember, this is absorbance, not transmittance. You would plot absorbance on the y and concentration on the x. And it turns out absorbance and concentration have a linear relationship. This is true up until you get to really high absorbances, because at some point solutions just can't absorb anymore. You'll get, I don't want to do that, 0.1, 0.3. Oh, that's terrible. Guys, just a little aside. Whenever you're writing decimals, always make sure you put a 0 in front of the decimal. This is hard to read. This is easy to read. Okay, that's just a little, I don't know, helpful hint. Right, and then you would plot here. Where did they go? They went to 0.9, 0.2, 0.4, 0.6, 0.8, and 1.0. You're going to have to do this on your problem set. So you plot the data. I'm going to plug in some points. So I know at 0.1 molar, I'm at about 0.072, which is down here. I know at 0.3 molar, I'm at 0.222, which is right here. 0.5, I'm at 0.355, which is right here. 0.7, I'm at 0.555. 0.9, I'm at like 0.651. Okay. This is freehand. You would never draw a graph freehand. On the problem set, what should you use to draw your graph? Excel. So, and put a line of best fit through. Surprisingly linear. And then you want to know where it is at 0.454. Absorbance 0.454. Go over here. So wait, sorry, could you repeat that? So are you allowed to use the equation Excel spits out and plug in? Absolutely. Absolutely. Yeah, there are a couple ways with the one in the problem set. There are a couple ways you could do it. You could find just like the slope of this line by taking 2 points, and that'll give you approximate slope. But these points aren't exactly linear, so you want to make sure you get the best fit of the line. Then from that you can get the equation. No, you can get the equation and have it displayed on your chart. Okay, so how do you get the equation? When you're doing Excel, you can click on the line, like right-click on the line, and then you can display equation on chart. There may be another step or two from there. Yeah, you can create a best fit line in Excel. That'll be something I can show you offline. So that's what I suggest you do for the problem set, is you plug it into Excel. Get used to using Excel. Any field you go into, not just science. My wife is in the nonprofit industry, and she does like project management and stuff. She uses Excel all the time. If you're going to business, you're going to use Excel all the time. Science, absolutely, you're going to go into Excel all the time. Medicine, you'll use Excel everywhere. So getting good at it now will save you a lot of headaches in college. Any questions about how we do this? Direct relationship between absorbance and concentration. All right. So what I would suggest you do, my battery is running dead. Okay. What I would suggest you do is you go through the learning objectives that are on the next few slides. And make sure you know all of them.